Okay, good afternoon, good morning, everyone, and welcome to the first talk of Canvas, Canadian Virtual Astronomy Seminars. When I came up with this idea, I had to come up with an acronym. Nothing in astronomy works unless it has a good acronym. So Canvas. The response from the community has been very good. I've got about 15, 16 people lined up to give talks, and the initial schedule is on the web link that I sent around in the email. So very pleased to introduce Tyrone Woods as the first speaker of the series. Tyrone is currently a Plaskett Fellow at the Hertzberg in Victoria. Tyrone got his PhD in physics from the Max Planck Institute for Astrophysics, and then went on to a research fellow position at Monash University for 3 years, followed by a prize research fellow at the University of Birmingham, and joined us in Victoria last year. So today, Tyrone will be talking to us about titans of the early universe. Take it away, Tyrone.
Thank you very much, Dennis. So yeah, I'm going to talk about high redshift quasars, I promise. But just as people filter in, I usually take the first few minutes to sort of do a little quick show reel of some of the great work that, in particular, some of the students have been working with, have been putting forward. So believe it or not, a lot of this actually has to do with interacting binaries, because if you only know me from high redshift quasars, you may be a little surprised to know that actually I started out working principally on interacting binaries and stellar evolution and problems like this. One of the papers that we just recently put out, I think is really, really cool, is by a grad student I've been working with back at Monash University, Adele Goodwin. I think this is her fourth paper, first, and that's just first off. It's coming out of a 3-year PhD. She's done outstanding work. Using a technique that she developed in order to very precisely, much better than before, measure the abundances in material accreted onto neutron stars in so-called type 1 X-ray burst systems. She's been able to find something remarkable about one of the prototypical objects like this SAX J1808. It's accreting apparently 50% helium from a 0.05 solar mass star, which you may know is just not doable from a 0.05 solar mass star in a Hubble time. This must have been a much more massive star once, which has since lost most of its mass to the neutron star and ejected. So we've been able to very strongly constrain the prior history of this object. It's really, really cool. This has just been published. I urge you to check it out. A lot of my other work has actually been on type 1a supernovae. These are thermonuclear explosions of white dwarfs. We know a lot about them, except awkwardly, we don't know how to actually make them explode, why a white dwarf should explode in the first place. The sort of standard textbook idea is that a single white dwarf accretes hydrogen or helium-rich material from some companion, growing slowly through nuclear burning until it reaches the Chandra-Sarkar mass and explodes. But this makes it a very luminous object, which is going to have a dramatic impact on its surrounding environment that will persist long after the source turns off, say, because it explodes. And so we've been able to use this to go and look for evidence of this sort of textbook model for how you make a type 1a supernova. And it's just not there. While we do know of a number of these objects creating nuclear burning white dwarfs, they don't seem to be making type 1a supernova. That doesn't mean they're not interesting for a number of reasons, just as probes of the binary stellar evolution, and also as probes of the interstellar medium. So a couple of students I've been working with have been looking at this. So Jere Kutula is in the second year of his PhD now, and he just put out a paper on a very interesting nebula ionized by an accreting nuclear burning white dwarf in the Small Magellanic Cloud, LIN 358. This has just been submitted, so watch out for that. And another paper by Diego Farias has been, he looked at a sort of more population study of objects in the Magellanic Clouds, where we see a nebula, studying that nebula, and where we don't, using it to constrain the density of the warm interstellar medium. It's a brand new probe of this sort of diffuse ionized gas between the stars. So both of those just recently submitted. Watch out for those in the archive. Okay, so you came here to hear about high redshift quasars. how did a guy who works on accreting stars and binary interactions get into the high redshift quasar line of work? Well, bear with me, we'll get there. The problem that first sort of drew me to this field was objects like this. We now know of accreting supermassive black holes, high redshift quasars, which reached 1 billion solar masses, even in some cases 10 billion solar masses, or of that order, well within the first billion years of the universe. We can measure the redshifts from the obvious spectral features, like with the position of the Lyman cutoff, and as well as the help of a few emission lines, and from the breadth of emission lines like the magnesium-2, we can estimate the velocity of the broadline region, and then applying a couple of scaling relations for the size of the broadline region, we can infer the mass. And we know confidently these things are roughly within a factor of 2 or 3 in this neighborhood. That's astounding. Because if you want to get, say, a 10 solar mass, 100 solar mass black hole, something that a POP3 star, some of these first stars in the universe, could actually make, you want to bring something at that mass up to 1 billion solar masses by redshift 7, you can maybe just barely do it if it accretes at the Eddington limit from the beginning of the universe right up until the moment we're observing it. Maybe just barely. And for the 10 billion solar mass quasar, no, I don't think we could do that. So something's wrong. Now, one idea is that you could sort of force feed these black holes with super Eddington accretion. And that's doable. You can at least certainly have brief episodes where you violate the Eddington limit. The problem is we think that these 10 to 100 solar mass POP3 stars, the black holes produced by these POP3 stars are probably quote unquote born starving. Now, what do I mean by this? Well, first of all, POP3 stars are very, very good at ionizing their surrounding interstellar medium, all of the gas around them and the halos in which they're born. Second of all, these objects will be born in clusters. Massive black holes born in clusters will sink to the bottom of those clusters, where through three-body interactions, they will very efficiently be able to kick each other out. So between these two, not having a lot of material to accrete and that isn't ionized, so it's really allowed to accrete, and easily kicking black holes out of the cluster, it's very, very difficult to get sort of these typical POP3 stellar mass black holes up to 1 billion solar masses by redshift 7, even if you invoke something like super Eddington accretion. So if we look at sort of the formula, everybody can see my cursor, right? Somebody give me a shout.
Yes.
Okay, thank you. So all of that talk about super Eddington accretion has to do with the efficiency of accretion, all of that. There's an awful lot of physics buried in this 0.1 when we look at the rough approximation for the growth timescale. If that's not going to cut it, the other way we can try and cheat and cut down the growth timescale is to start with something much more massive. Now, there are a number of ways that we think you can produce a very, very massive seed for a supermassive black hole. This is sort of a classic Rees diagram. Lord, Sir, Martin Rees, or Sir, Lord. I'm not sure. I'm not very good, not much of a monarchist. But this is a rough summary, at least from a 1980s perspective, all the different ways you might be able to make a supermassive black hole. And I love this diagram. I always try to have it relatively near the start of my presentations on this, because whole careers have been devoted to tumbling down just a couple of the different sort of routes along this pathway. We don't talk too much about sort of relativistic clusters anymore for a variety of reasons, but this side of the diagram remains very popular. And in particular, you'll notice a very, very prominent object which several routes seem to pass through, called a supermassive star. Now, what do we mean by a supermassive star? Well, sort of in more modern parlance, this is usually referred to as, and there are a couple of different variations on this, but the direct collapse scenario. This is a more modern version of this plot by Mar Mescler. Was at the University of Montreal at the time, is now back at Barcelona. And basically this sort of takes this diagram and breaks it up into the redshift that we expect these things to form and how we expect them to evolve over redshift, and what kind of masses we expect them to produce if they get a chance to keep growing, or if they end up isolated, what kind of leftover intermediate mass black holes we might be able to hopefully find today. And so, direct collapse black holes, these are these supermassive seeds, things that are of order 10,000, even 100,000 solar masses. Star-like, is it just a gas cloud? We'll get to that. A massive object collapses and gives you a head start. So you drop a few E foldings before that would otherwise be needed before redshift 7. Everybody with me so far? I find with the Zoom meetings, it's extra important to ask.
Yes.
Okie doke. So again, what do we mean by supermassive? Well, sort of in the classic picture actually goes all the way back to the 1960s, when people first sort of conceived, okay, what's the very most massive star we could ever possibly make? And they started to come up with numbers around, barring things like pulsational instabilities, etc., which we'll get to. One sec. Okay, thank you very kindly. Just getting the phone, sorry. So, endless surveys. So they came up with a number around 10,000 to 1,000,000 solar masses was sort of the number that you would need. Initially, the hypothesis was sort of driven, again, this is the 60s, early 60s, by what you would need in order to sort of power, satisfy the energetic requirements for something like a quasar. And of course, now we know very much that these are supermassive black holes. But the idea kind of hung around, and you see it in the Reese diagram, as a way you might be able to form the seed of what would eventually grow to become a supermassive black hole. So to understand the physics of what happens when you try to put together an object and hope it maybe lives as something like a star, when you get into this kind of mass regime, you need to look at the pressure support, first and foremost. As you move to more and more massive stars, more and more of the pressure support holding up the star is dominated by the radiation pressure. The gas pressure becomes smaller and smaller until when you get to these very, very, very massive objects, gas pressure is just a tiny, tiny perturbation. And this means that the star, in an idealized sense, if you allowed it to thermally relax, would look very, very much like a polytrope of index 3. Or another way of putting it, the local adiabatic index would be 4/3, plus a very, very small perturbation, which depends on the gas pressure. Now, if you think back and remember your stellar evolution lectures, an object with a adiabatic with a gamma roughly of order 4/3, very, very close to 4/3, is a very, very scary object because it is forever trembling on the verge of instability, as they noted back in the 60s. Just a very, very small perturbation. This is a very, very marginal against collapse. A very, very small perturbation is going to be spell destruction. And so the kind of typical perturbations that you might expect, to need to include would be things like rotation and magnetic fields. And yes, these are very important and interesting, and we'll get to them hopefully by the end of the lecture. But something that you wouldn't naively expect would be important, but turns out to actually be extremely important, which seems crazy, because this is naively you look at a star like this, you say this is very much a Newtonian object. We can safely ignore general relativity, right? Well, if you include post-Newtonian corrections, there is a small correction that you must include due to the change in the effect of gravity pressure gradient to the gamma 4/3 that slowly grows with mass. However, there is also a correction as you move to greater and greater masses. The gas perturbation, which you're comparing this with, falls. The total fraction of the pressure, which is due to the gas pressure. If you compare these two, there is a point at which they meet, at which it is simply impossible to have a hydrostatic star. This gives you a nice criterion as a function which with a cutoff in mass that, depending on exactly what you assume about the structure of the star, comes out around 10 to the 5, 10 to the 6 solar masses. And so this was the sort of original construction of a supermassive star, the idea of what it means to be supermassive, that it's not going to be able to live as a star beyond this point. It's just going to immediately collapse into a black hole. Everybody with me so far? I'll keep moving, but please jump in with questions. Any questions? Yeah.
No, I was just saying.
Oh, okay, cool. Yeah. Okay, so this is sort of the 1960s picture of how you might be able to, put together a gas cloud that could collapse to give you a massive seed, and about how massive it would need to be to just directly collapse. More recently, the trouble is it's not immediately obvious how you might be able to produce such a thing. And so, maybe the classic idea was you have sort of a runaway collapse of a dense cluster of stars. As three-body interactions kick out stars, they take away kinetic energy from the system. The cluster contracts until you get sort of a coalescence and merger into one big fluffy object. The trouble is that if you try to do this numerically, and at the end we'll come to some tricks where you might be able to make this work, but generally speaking, that's a very lossy way to try and grow a massive cloud that can collapse. You generally sort of tap out at about a few thousand solar masses, which helps a little, but it doesn't really solve your problem of trying to get to 1 billion solar masses by redshift 7. There's still just too many E-foldings in there. So the other idea of how you might be able to make a massive object that's been gaining a lot of ground, and I would go so far as to say it's one of the leading contenders at the moment, is this sort of atomic cooling halos picture, often synchronized atomic cooling halos, which works a little something like this. This diagram is from John Regan, although the idea goes back a little bit further. So essentially, we have two primordial halos, zero metallicity gas, in relatively close vicinity. One is a little bit ahead in its evolution of the other, condenses, fragments, produces a population of POC3 stars, zero metallicity stars. The other halo is lagging a little bit, just stochastic chance. Now the universe isn't reionized yet. This is happening out at redshift 15, 20. So the ionizing radiation is sort of confined locally near these POC3 stars. But the Lyman-Werner radiation, that molecular hydrogen dissociating radiation, that can stream freely and irradiate the other halo. Under the right conditions, it can destroy all of the molecular hydrogen in that halo, which is going to have big repercussions because in a primordial environment, you don't have metals, you don't have a lot of molecules other than H2. That's your primary coolant in the halo. And so if you destroy all of it, as the cloud contracts, it's going to heat up and heat up and heat up until it activates atomic line transitions from hydrogen. This happens at around 8,000 Kelvin. But both the Jeans mass characteristic mass of stars formed. And the infall rates, the rates at which we expect these stars to grow, scale with the temperature to the 3/2. So as you jump from tens, hundreds of Kelvin up to 8,000 Kelvin, suddenly you boost the kind of masses you expect to be able to produce up to of order 10 to the 4, 10 to the 5 solar masses, and infall rates to the neighborhood of 0.1, even 1 solar masses per year. And this, we think, is how you might be able to rapidly produce a single massive object that can collapse to form a massive direct collapse seed black hole. The trouble is, if you want to understand what this object is going to do, all of the polytropic ideas that I was, 1960s ideas I was going over before, these are useful for a very crude intuitive sense, but it's not what these stars are going to look like. And the reason is because these rapidly accreting supermassive stars don't know how to relax. What I mean is, the accretion timescale is always going to be shorter than the thermal relaxation timescale for these stars. So they're never going to be in a nice thermally relaxed state. We need to actually run detailed stellar evolution calculations. And so a number of grids of models have since been done. I'm going to focus mainly on results using the Kepler stellar evolution code, just mainly because it's what I was using working with Alexander Hager at the time. But there have been results with Geneva, with Meza, with others. So in brief, this is an implicit Lagrangian hydrodynamics and stellar evolution code. We include post-Newtonian corrections. We can drop down to very short timescales if you start to see an instability forming, if there's some significant gradient in one of the key properties. Kepler was actually one of the earlier codes to try to model the sort of classic idea of how these supermassive stars would evolve. But there have been, going back to the 80s, but of course there have been many upgrades to Kepler since the 80s. We now have a full adaptive nuclear network, including accretion and following these things from relatively low masses as they grow to become supermassive. So as an initial sort of trial run, if you will, and to sort of get a feeling for what these objects are, let's start with some initial conditions. We'll begin our models with just sort of 10 solar mass, fluffy, high entropy, relatively high entropy protostars with primordial composition, not thermally relaxed, not nuclear burning yet, and we'll try accreting constant accretion rates that are sort of roughly bracketing the range of accretion rates we would expect in this atomic cooling halo picture. And I will jump to one punchline, which is you might immediately be thinking, oh, does this, if we started with 1 solar mass or with 100 solar masses, does it significantly impact our results? And what we found is that no, when you're accreting 100,000 solar masses, it doesn't so much matter if you start with 1 or 10 or 100. So here's a Kippenheim diagram of what one of these objects looks like. So if you haven't seen a Kippenheim diagram before, essentially what this is it's a snapshot, a series of snapshots over time across the enclosed mass of what's going on within your mass shells at each point in time. So we have sort of, with the green single hashes here, this is the thermally relaxed convective core that sort of looks the most like our naive, the part of the star looks the most like our naive polytropic models. And sitting on top of that is the ever expanding, rapidly accreting, never getting to thermally relax, to fully thermally relax, inflated envelope. And this ends up being a significant fraction of the mass of the star. The purple shading here, this is just a nuclear burden. So we have this very different structure. In a polytrope, you would expect this thing to be wholly convective all the way through. Here we see convective core, massive, fluffy, radiative envelope. what does this mean for ideas about how massive a star could actually get? What does this mean for things like our Chandrasekhar criterion or Post-Newtonian criterion or Chandrasekhar finding? There are a lot of different names for this relativistic instability that leads to collapse for supermassive stars, mainly because there are just too many instabilities named after Chandrasekhar. So revisiting this, we had this criterion. We can plot either side and look at where this criterion is violated, where we would expect collapse to occur. And we did this for our 1 solar mass per year model, yes, at plotting both one side and the other, sort of the gas pressure perturbation and the post-Newtonian correction at 100,000 solar masses and 320,000 solar masses, which is roughly before the object collapses. And sort of the solid line is one side of the criterion, dotted is the other. When dotted exceeds solid, you would expect a collapse. Now at 100,000 solar masses, this happens way out in, this is the convective core, note it's a log scale. This is the sort of fluffy, odd-looking radiative envelope. It only violates it out there. Well, we don't really expect our polytropic criterion to work where the star is very, very poorly described by n equals 3 polytrope. So, okay, fine. But even when you get to 320,000 solar masses, where it exceeds it, you see red and red here compared, well within the convective core, we still actually, the star survives for another, I think about 1,000, 10,000 years. This is all basically to say that, you know, if you look at this criterion, it was derived, this coefficient 1.12, assuming this thing was a perfect pencil and paper n equals 3 polytrope. This goes back to Chandrasekhar's work in the 60s. That's not really describing what we're looking at here. Maybe very approximately the core, but really you need to run detailed stellar evolution models in order to figure out what these objects are actually going to look like and what they're actually going to do. So we did this for a grid of models. And we actually were able to work out for the first time what the final massive collapse with the fate of these objects was systematically as a function of really the most important initial condition, which is the infall rate, the rate at which they grow. And so we've shown this here. The gray shading delineates objects that, the darker gray here, that collapse after hydrogen has been exhausted in the core. So these things actually live a substantial fraction or even most of their nuclear burning lifetime, which I think is amazing. Versus these objects which collapse at some point, these more massive ones, they collapse at some point during their main sequence. There's a nice fitting relation for this here. The key here is that we have sort of a definite boundary between very, very, very massive stars and the truly supermassive. Now, there are a number of other complications to this. One of them that I mentioned earlier is, of course, rotation. There's a known problem from trying to grow POP1 stars up to very, very large masses, which is that if you're accreting mass, you're also presumably going to be accreting angular momentum. And the problem is if you're trying to accrete a lot of mass, you're going to accrete a lot of angular momentum. And that's going to spin this thing up, could conceivably spin these stars up to the point, to the breakup limit, to the point where they're shedding mass. This problem becomes, we have here a derivation just of what the critical velocity rotation rate would be. It becomes an even worse problem if you account for the fact that these things are very, very close actually to the Eddington limit, very, very massive stars. So there's an additional lifting pressure, which makes it actually even more stringent. And so we can ask ourselves, and we did this, if these supermassive stars are accreting angular momentum, let's say just matching the angular momentum of the inner edge of the accretion disk, assuming it's Keplerian, how much angular momentum could they actually be accreting versus how important does some kind of magnetic braking or disk instabilities or some other mechanism need to be in order to avoid this thing just immediately spinning up to breakup? And it turns out you need to get rid of about 99% of the momentum, which sounds like it's putting this idea to bed. And I was initially very concerned as well, except for the fact that this is very similar. You know, it's maybe more 90%, not 99, but it's a very similar to the kind of problem that, again, we do see in forming massive POP1 stars today. And the answer is you really do need things like magnetic braking and gravitational torques, disk instabilities, bar instabilities, things that can pull angular momentum out. Early work on this, including in a paper by Lino Hemmerle in 2019, suggests this is roughly promising. We do think that with the kind of magnetic fields we expect these stars to have and pulsational mass losses of the order that we expect, we should be able to get the kind of braking that we need. One thing that I sort of skimmed over. So you may be worried about pulsational mass losses. These objects should be very pulsationally unstable, and the short answer is yes. We do think that they lose of order 1,000th of a solar mass per year due to pulsational instabilities, based on state-of-the-art calculations by Hosokawa et al. But of course, if they're accreting 0.1 to 1 solar masses per year, this is relatively negligible. And we don't expect there to be any winds since these are primordial stars. Yeah. Oh, and one other caveat that I think I have a little bit of time, so I'll just quickly mention. We also only used constant accretion rates, so we have tried this, and others have also tried this with variable, more realistic accretion rates fed by 3D detailed simulations of contracted halos. And the answer is, as long as the accretion rate doesn't vary on a time scale much longer than the thermal relaxation time scale of these stars, then they proceed as normal. If you simply take the time averaged accretion rate, that is roughly lines up actually rather well with our calculations. Of course, if you do have variations in the accretion rate much longer than the thermal relaxation time scale, then what happens is this big fluffy very red supermassive star that we were evolving contracts and becomes blue, becomes an ionizing source, and then you have a host of other problems. But maybe we can get to that in the questions. Okay, so this is an awful lot of theory. We wanted to take that theory, a lot of stellar evolution theory, and bring it together with people working on observing high redshift quasars, people working on modeling the 3D evolution of these primordial halos to begin with, people doing trying to model populations of these objects. We brought them all, a number of them together for a workshop in Italy in very late 2017, and it was great. It was a heavy focus on trying to hunt for observational diagnostics, ways that we could actually take this from theory and make this put this to the test, make experimental observations. And so we compiled this all together. I'm not going to be able to get to everything in the talk, but if you're interested, I urge you to check out our invited review paper that we put together on the subject, which finally came out late last year. Okay, so before I get to future observational prospects, any questions? Going once, twice? Okay, I'll move on then. So, what is going to be, the slam dunk? What's going to be the definitive way that we will know for sure that at least some supermassive black holes arose in the early universe from something like some variation on the direct collapse black hole channel, massive seeds. One idea that I think is very promising, although a little bit tricky, will be simply waiting for LISA to eventually fly. So the Laser Interferometer Space Antenna. If we're going and hunting for gravitational waves from merging massive black holes in the early universe, there's a certain formation rate, a growth rate, that we're expecting just from the normal merger of halos in the early universe, the famous prediction is from Susanna et al. 2007, and it sort of really turns on by redshift 15 and proceeds from there. If we actually expect stars to be originating through these atomic cooling halos, one thing that I sort of skimmed over, we say we have a Jeans mass in the neighborhood of 10,000, 100,000 solar masses. And we would expect, I've been assuming one so far, massive object to be formed per halo. But the truth is, we probably expect, and in fact this is borne out by a number of simulations now, on the order of a few, several even, very massive to supermassive objects are going to be formed. When these collapse to black holes, you have the prospect of being able to form massive black hole mergers, if the conditions are right in the halo, much earlier than expected, even well before redshift 15. These are the solid lines. Now, the different solid lines here correspond to sort of different expectations for the fraction of multiple direct collapse black holes that we expect to form in these halos, and what kind of irradiation is needed. What is it a typical irradiating environment, or do you need some really special, really synchronized picture in order to produce an atomic cooling halo? But for sort of modest assumptions, we expect something in the neighborhood of 0.6 mergers per year, or in the lifetime of LISA, we would expect of order a few. So this if we detect that massive black hole mergers at these extreme redshifts, I think that would be a pretty maybe not definitive, but very close to a slam dunk. But I wouldn't mind if we were able to come up with a more definitive test a little bit earlier. At least it's going to be a while away. So with that in mind, there are a number of other tests that have been proposed. Something that we've been working on is we'd like to try and look for the supermassive stars themselves. These things are going to be of order a few 100,000 solar masses. If they're radiating at the Eddington limit, it should be possible to find these things. So we've been taking our models, assuming they radiate as black bodies, taking from 3D simulations of the halos that should be feeding these objects. We then take spherically average density profiles, and then we've been using Cloudy to model how this radiation from these supermassive stars would be filtered through these halos in an approximate sense, in order to get an idea of what the spectral properties of these objects would be like. This has been work led by a student at the University of Portsmouth, Marco Sirachi. So he's produced a number of predictions for Euclid, etc. I'm going to focus on the predictions for NIRCam with the James Webb Space Telescope. Here for sort of rapidly accreting 0.1 solar mass per year is the dashed lines, and 1 solar mass per year is the solid lines. The AB magnitudes that we'd expect in different NIRCam bands. And you see that, as a function of redshift, it's going to be very faint. Grant, as a rule of thumb, as an idea, 31 here, that's roughly 25 hours-ish. So that's a lot of time to ask for with James Webb. But there's a couple of things in our favor. First of all, we can piggyback off of surveys of lensed and strongly lensed environments, and this is something we're hoping to do with already existing guaranteed time observations like Canucks. And the other aspect that's handy is that if we really do expect a large fraction of supermassive black holes to come about through this channel, then you expect these objects should actually be relatively common, and you just need something that can look deep enough in the near infrared in order to find these. Somewhere, at the uppermost bound I've seen in terms of predictions for rates integrated across all redshifts, just as an area on the sky, you would be expecting something in the neighborhood of 1 every few NIRCam fields. So very quickly, we should have an idea early in the lifetime of James Webb whether this channel is actually common, or whether it's maybe more only the rarest, only the most massive and earliest supermassive black holes can come about through some channel like this. So, can we directly detect these supermassive stars? Yes. Will we? Still very much an open question. Another tricky bit, if we don't find them right away, is that James Webb has a very, very tiny footprint. Ideally, an ideal hunt for these objects, if they are relatively rarer, would be to go hunting for somewhat lower redshift supermassive stars with Euclid, and try to come up with some kind of color selection tool for candidates, and then do spectroscopic follow-up on the most promising candidates with James Webb to try and confirm these. So I mentioned formation rates, but actually there is one more intricacy. It's not just the rate at which they form, right? If we want to know how many should be out there at any given time in our prospects for actually detecting these objects, but also their lifetime, how long these objects live. Now, for the rapidly accreting models that I showed before, you can actually infer it from one of the plots I showed before. If you're getting up to tens of thousands to 100,000 solar masses, accretion rates of 0.1 to 1 solar masses, you're expecting these things to live tens of thousands, even up to actually 1 million years. But that's just in the sort of rapidly accreting scenario. This what we generally think of now as the most promising interpretation of the direct collapse scenario. But we also have, collapse of dense stellar clusters. There's also another model that I didn't talk too much about, and I don't think I'm going to have time to talk too much about, which is this model by Lucci and Meyer et al., mainly Meyer and Benoli, where you have maybe if you have unusually gas-rich massive protogalaxies merging, then at relatively late redshifts, you could maybe get the conditions for very, 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 very rapid infall. I won't talk too much about that, but these are sort of some of the other ideas, besides, of course, rapid sustained accretion onto more typical POC3 stars that people have been talking about. So, how long do these objects that are produced by dense stellar clusters, how long could these actually live? Again, these are things that are formed by shedding mass from three-body interactions. It's hard to get to things that are of order beyond a few thousand solar masses, but you might be able to do it if you, and this is, I think, kind of neat, if you have sort of a hybrid cluster collapse and direct collapse black hole, atomic cooling halo, kind of rapidly accreting star kind of model. So the idea is, as you bombard this central object stars as the cluster contracts, if it's accreting rapidly enough, it will actually may inflate, much like a more typical atomic cooling halo rapidly accreting supermassive star. This is going to make it a much bigger target for sweeping up, a much larger cross section for sweeping up other stars in the cluster. And so this might be one way, sort of a hybrid way to try and exceed that and actually get up to things that are of order 100,000 solar masses or more, which will then thermally relax and produce something more, maybe more of a typical supermassive star. So how long do these things live? Well, generally the answer is very, very long, relatively speaking. I mean, compared to what typically when you think of direct collapse, people would imagine something which is just going to collapse on its dynamical or maybe thermal timescale. Here we're seeing things that live a million, 1.5 million years, surviving beyond core helium burning, or around 100,000 solar masses, dying when they end core hydrogen burning. It's only if you could possibly produce something more massive than 150,000 solar masses, and then allow it to thermally relax, that you could produce what I would call a quote unquote true direct collapse, a genuine cheat to get 100,000 solar masses, hold 100,000 solar mass seed, and not really have anything that you expect to observe as the progenitor. And frankly, not to put too fine a point on it, but it really doesn't seem possible to produce something in that range model, which could then be allowed to thermally relax. This is all for primordial composition. Pavel Denisenkov and others have done similar work and very interesting work trying to look at non-zero metallicity supermassive stars and looking at other interesting prospects like other observational signatures like maybe enrichment from these objects, but I'm not going to go into too much of that today. So one more final thing, just to sort of try and well, second last thing, try and round out our survey of all the different ways you might be able to make a supermassive star, how long they could live, and what you could look for to prove or disprove that these things are actually out there. And so we had a recent paper that this one, Lionel Hammerly at the University of Geneva led, just sort of looking at the overall parameter space for any given accretion rate as a function of the mass of the object you're accreting onto. Is this thing going to be able to live on in hydrostatic equilibrium, or is it going to hit the general relativistic instability? Will it simply undergo a quote unquote dark collapse where it doesn't live for a long time? Is it going to be some kind of unusual object? I didn't have too much time to talk about these hylotropes. These are objects proposed by Begelman et al. And sort of, you may, if you're familiar with a Thorne-Zhitkov object, is sort of those are neutron stars with sort of red giant envelopes on it. This would be sort of a black hole with a very fluffy envelope over top of it. Very, very, very hypothetical objects that I won't get too much into here. But in principle, we can delineate at least the boundaries where if you wanted such a thing to make, if you wanted to make such a thing, these are sort of the regimes we're talking about. So scaling back a little bit, I've been working with John Regan and John Wise and a few other people, trying to look at sort of more typical POP3 halo star formation, and these irradiated atomic cooling halo, atomic cooling halos, and sort of everything in between. So in principle, you should have a kind of a continuum from completely destroying all of the H2 to normal POP3 stellar population. In between, you may have some catalyzed growth of POP3 stars. You may be able to make more massive and even somewhat rapidly accreting population 3 stars, or rapidly accreting supermassive stars, but whose accretion is cut short. And this is sort of what we're finding, and I think it's very interesting. We should have our first paper on this out very shortly, and expect a number of other papers to come in the very near future. So I think I'll wind down there, so there's a little time for questions. But the general punchline is, direct collapse black holes, these probably arising through these atomic cooling halos, although there are alternatives, is a viable mechanism for producing direct, massive seeds of high redshift quasars. Whether it is the mechanism or not is going to have to be put to the test observationally. But we're building the tools today, and in the very near future, within the next few years, we're going to be able to start to make very strong statements about whether these things are common, whether this is a typical channel, or whether this is at most only a relatively rare way to make supermassive black holes. I think that would be very surprising, given the way that sort of the literature has been evolving, but we've been surprised many times before. So I'll stop there for questions. And if you're interested in any of this, Woods is almost ungoogleable. There are just too many of us. So shameless plug, do check out my website. Thank you.
Thank you, Tyrone. It was very interesting.
Thanks.
Okay, we have time for questions. So I see Chris Matzer. Chris, go ahead. You have a question.
Yeah, Tyrone, great talk. I wanted to ask, could you remind us what you were assuming about the entropy of the accreted matter? And also the second question was, did you, in your modeling, just assume that the rotation was completely negligible, or did you account for it to some
Very good questions. So regarding the entropy, so you need to have some kind of make some kind of assumption about the conditions of the matter, that, you know, the temperature and the density, the entropy of the matter that you're accreting when you're trying to revolve these stars. So what we did is we actually matched it to the entropy just slightly within the outer layer. We ran into a lot of weird numerical instabilities and noise when we matched it to the very outermost layer. So effectively, we sort of assumed that the matter was accreted and kind of sank in just to a very, very, very modest optical depth. And that's what we assumed about the entropy of the accreted matter. For rotation, for all of the models that I showed, yes, for all of the plotted models that I showed, we assumed negligible rotation, no rotation. So if you do include rotation, we did find that, you know, you can with a couple of models that we did run, it looked like you can somewhat exceed the masses that we were able to find with the non-rotating objects. But things got very complicated because you also, you know, to have them grow at all, you needed to throw away lots of angular momentum, and so there was a lot of tunable. There was, I think, a bit too much tunable parameter space to make, you know, a very neat and tidy plot for the time being. But we did find some interesting things. Although you can't make a very surface rapidly rotating object, you can make a very strongly differentially rotating object, and this could have very interesting consequences if you want to imagine ridiculously overpowered gamma ray bursts and things like that.
Shantanu, can you go ahead and ask your question, please?
Hi, thanks. Yes, nice talk. I had actually a similar question to Chris's second part, which you just answered. So just to expand on that a bit, your chart of formation mechanisms included this collapse through a bar-mode instability, which of course could occur if there's sufficient rotation. You also mentioned that the SMSs have to be slow rotators. So I presume no detailed calculations of bar instability and collapse have been done yet, but I want your comments on the probability of that formation channel based on what you know, and would it have observational consequences?
I think that it's very complicated, and I think I hesitate to speculate too far, but I think that what would you be able to do? Well, it would be very, very interesting, of course, if you have, you know, if you do genuinely have like a split into a binary, then in advance, you know, through some bar mode instability, in advance of the collapse to black holes, I think the most exciting thing, of course, would be if you had an interaction between, say, one that's collapsed to a black hole and the other that maybe is still a star. I think it would be very exciting to have supermassive X-ray binaries. Otherwise, yeah, I'm not immediately sure offhand. But it's a very, very, very interesting direction for future research. I think you know, that's why I love this diagram. There are so many different directions you could go.
Okay, thank you. Any other questions for Tyrone? I don't see anybody's hand up.
I have a couple of questions.
Okay, go ahead.
Yeah, so the first question is, do you think there'll be any observation, any way to observe the seeds and know from which channel they came? Because it's always like starting from 10 to the power 4 or 10 to the power 5, but is there a way to know if it is a DCBH seed or it came from a collapse or it's like a collision between the stars in cluster?
Sure. So it depends on a few factors. It's not going to be clean cut, but I do think it's doable. So basically, if you, in the naivest way of looking at it, if you do, or simplest, if you do have a direct collapse, if you do have a rapidly accreting object, it's going to be very, very inflated. I talked about trying to hunt for these objects. They're going to be relatively red. They're going to be, but very, very, very luminous. Versus if you did have something like a the collapse of a cluster to form a maybe more 10 to the 4 solar mass object, or a few times 10 to the 3. This is going to be, assuming it has time to thermally relax, much more towards the blue. And so this would be, a very obvious observational distinguishing characteristic between these two objects. There are a number of other ideas that have been proposed. I mean, you can have people have talked about, okay, what if it ends up being too hard to find these supermassive stars right off the bat? Well, you could try to look for massive black holes in very, very undermassive hosts, grossly violating, sort of black hole galaxy mass relations. And this might be one way to identify, the direct collapse black holes, at least from the POP3s, depending on how massive it is, maybe direct collapse versus cluster collapse. But I think another way would be, if gradually over time we start to build up some kind of understanding of what the masses and even eventually mass distribution of intermediate mass black holes really were, that would probably, you would get into a lot of entanglements with population synthesis of these objects, and I could imagine a great couple of decades of debate in the literature about it. But I think that would be definitely a good way to try and suss this out. Oh, and of course, if you do see black hole mergers at high redshift, at very, very high redshifts, well above 15.
Okay, thank you very much. Yeah, that's. Do you have this discussion like in one of your papers? Because I'm doing similar work and it will be relevant.
Yeah, for sure. I would start with the review I shamelessly plugged towards the midpoint there. Yeah. So you can find it from that, or you can find it on my website. And
okay, perfect. Thank you.
And if I know anything, it's probably in that. So.
Okay, perfect. The other question was about the accretion model, because the mass growth will highly depend on what kind of accretion it's doing. Is there a good way to know what kind of accretion going on? Like if it is bondy, it can accrete mass really fast, like within few.
Yes. No,
Yes.
I mean, presumably it will be, I always think intuitively when I imagine it, I kind of assume it must really in practice be accreting through a disk. But the truth is we just don't have, you need many, many more orders of magnitude in resolution than is presently really available in most simulations to model the halo and all the way down to the inner parts of the disk. So, generally what you have to do is this is broken up into several different simulations, but then you're introducing your biases when you do that. So naively, I would just say I don't exactly know really what the accretion column looks like, but one would imagine a disk.
Yeah, perfect. Okay.
Next question from my neck.
Hi, I'm kind of wondering what could be like a typical Eddington ratio for the supermassive stars, because I kind of assuming them to be highly accreting.
Mm-hmm. Oh yes, they're the supermassive stars. So the supermassive stars are very rapidly accreting, but they're very, very inflated. Out to 10 AU in that neighborhood, 1 to 10 AU kind of thing. So you don't get the kind of energy release that you would get from, say, a if you're accreting onto a black hole by any means. And so the Eddington ratio is not as high as you would assume. The stars themselves are very, very near the Eddington limit, but that's a different factor.
Okay, that makes sense. Thank you.
Yeah.
Okay, I think we'll wrap it up there. Thank you, everybody, for very interesting questions. Thanks again, Tyrone.
Oh, thank you very much for having me.
For a very interesting talk. So next week, we will be joined by Paul Weigert from Western University. Topic a little closer to home on interstellar comets and asteroids. So hope to see you next week. Anyways, take care, everybody. Bye.
Thank you very much.